than it is any kind of formula or anything. And what Newton's first law is all about, and I'm going to refer to inertia up there when we get to it, is that inertia is the property of matter that causes it to resist changes in motion. And so in the world, in Earth, or anywhere in the universe, things just want to remain the same. So what Newton's first law states is if there is no net force, so there might be forces, but there is no net force, so they might have forces canceling each other out, acting on an object, the object will remain at rest or will keep moving at a constant velocity. So if your object is just sitting there, unless your net force acting on it is bigger than zero, one direction or the other, the thing is just going to sit there. Now, another example, if something is moving at a constant velocity, which means it's not changing its direction or its magnitude of speed, then it will keep going unless something stops it, like friction, some applied force, gravity, lots of different forces that can affect an object. Now, a weird example of an object that's moving at a constant velocity and will keep going is space junk. Space junk is a great example, is if something is floating in space, it will just keep floating because there is space. It will just keep going. And one of the crazy examples that I give out is that if you were to say travel into space and you threw a baseball towards, I don't know, space, that baseball would not stop moving. And so theoretically, your great grandson or daughter, 600-700 years from now, could jump on a spaceship and catch a baseball that you threw. I'm getting glitchy, am I? Is that in sound or just in vision? Both. Oh, great. What am I going to do? Well, I'll keep her going. I'll try my best here. All right. So I guess I'll do a lot of explaining with the words here because I just don't, I'm not able to switch here. See, I'll go as slow as I can. Example one, pushing a very large rock and it remains at rest. And so what that would mean in that situation is whatever your applied force is, it's going to be less than your force of friction. Am I still glitchy?
Yeah.
I am, eh? Even voice. Really, that's weird. That's a first. I'm going to come in. I'm going to try to leave the meet and come back. All right. So I'm going to leave the meet and come back, see what happens. So here we go. All right, perfect. Thank you for telling me that. How are we looking now in terms of vision and glitchiness? Good. All right, so it's working now. All right, perfect. Okay, so again, Newton's first law, if no net force is acting on an object, the object will remain at rest or will keep moving at a constant velocity. So if you're trying to push a very large rock and it doesn't move, that means that whatever force you're applying is less than or even equal to the force of friction that you're applying. And that is why that rock will not move. So you keep applying the force, the rock keeps applying friction. So that you cannot move it at an equal amount. And so they can either be equal, or in terms of a very large rock, it can be much greater. But it's always there matching your applied force, and so it doesn't move. Your net force equal to 0. Another thing we could have here is example 2. If a car hits the brakes really hard, the people inside the car keep moving forward. Of course, if they don't have a seatbelt, that's really dangerous. And so what happens is the body of a person, they wants to remain at the same velocity. And so when you hit the brakes, the car is stopping, but the people are not. Whoops, velocity. There we go. All right, so that is an example of Newton's first law. Now, how do we apply this first law? Again, it's usually applied to different questions, but as a group, but just in a single way. Example 3, I have a diagram on the right here, shows an object that is moving at a constant velocity of 4 meters per second. All right, constant velocity. Find the force of gravity acting on the object. So there's Fg. All right, we have F1 and F2 on our way up. But here's the key here, is that it is at a constant velocity, right? So that means your acceleration is 0, which means F net is equal to 0, which means that if I add up all these forces, so I have F1 plus F2 plus Fg, they all have to equal up to 0. All right, now, if I add those up, again, I have a 0. Again, as in terms of direction, I always say up is positive, down is negative. So F1 would be at positive 10. 18, F2 would be positive 18 because, again, it's up. And whatever Fg is, it's going to be minus because it is directed down. All right, and I can, well, I'm going to move Fg to the opposite, a negative Fg to the opposite side, so it becomes positive. And, well, on the other side, I'm going to have a 10 and an 18. And so that would be 28 newtons, would be the force of gravity. Again, because the net forces, and we all I have here is the vertical forces, have to be 0, again, because it's at a constant velocity. And so our force of gravity is 28 newtons. All right, now that's Newton's first law. Again, a lot of these laws, well, this is our big law coming up here, is Newton's second law. Used quite a bit in conjunction with the first law. And that law says if the net force on an object is not 0, right? That was all, the first law is all about when it is 0. Now it's when it's not 0, the object accelerates, so it changes its velocity in the direction. Now this is kind of stating the obvious, but when Newton was around, this wasn't obvious. The acceleration objects in the direction of the net force. Right, so if you push it to the right, the object's going to accelerate to the right. I think that's pretty obvious, but again, not when Newton was around 300-400 years ago. And so what we're looking at is F net, your net force, is equal to your mass times your acceleration. And again, acceleration is a vector, just as your net force is a vector, magnitude and direction. And so, example 4, find the net force of a 5-kilogram object that accelerates at a rate of 3.8 meters per second squared east. And so, well, I'm going to use my formula here that I have up top. F net is equal to mass times acceleration. Again, everything has to be in standard units, which I have here. So 5 For my mass, my acceleration, again, is going to be that 3.8 meters per second squared. East. All right. Now, when I multiply those, my net force will be times it by 3.8. Per second squared forward. Again, your net force and your acceleration have to be in the same direction. It's glitching and I froze again. All right. Doing my best here, folks. All right. So again, I'm going to use my F net is equal to my M times A. All right, so I'll try to do more explaining with my diagrams here, or my information that I've got on here. All right, now your F net, we have it right here, force of 480 newtons forward. So I got 480 newtons forward. And again, our acceleration is 1.5 meters per second squared. Per second squared. And again, that is, whoops, lead forward. Oops, there we go. And again, your net force and your acceleration are in the same direction, right? Because again, if you push something to the right, it's going to go to the right. If you push something up, it's going to go to the up. Now, again, the first thing, I'm going to divide by my numerical coefficient here. I'm going to divide each side by 1.5. All right, and so those divide each other out. And my mass, which does not have direction. All right, I'm going to divide those two together. Let's see, 480 divided by 1.5. I end up with 320. And again, the standard units, this mass would be in kilograms. All right, now we're going to step it up here a little bit. All right, so I get to example 6. All right, so a sports car is traveling at 28 meters per second west. When the driver applies the brakes and the car comes to a stop in 3.5 seconds, the mass of the car with driver is 12,000 kilograms. Big thing. What is the force of friction being applied by the brakes? All right, so the car is just moving along. So here's a free body diagram of our car. All right, it is just moving along, and we have this force of friction. Now, that is the only force other than the brakes. The brakes are applied, and so our force of friction is actually our F of net. Right, and this again is our 12,000 kilogram vehicle. All right, now, what other information I have? I have my 28 meters per second. That's what it's traveling along. So that is my VI is 28 meters per second west. All right, it comes to a stop. That is my VF. All right, what else do we got? Oh, time, which is my delta T. All right, so there's our information that we know. Now, we want to find F net. All right, that's what we're trying to find. But it equals MA. So we have the mass, but we need the acceleration. Well, we have this information over here from our motion equations so that we can find the acceleration first. So we're going to have to find the acceleration first. And so I look at my motion equation sheet. Thought some of you probably thought that we're done with that, but we're not. And so we have, well, I look at the first equation and I can find acceleration because it's equal to, in my formula, VF minus VI all over delta T. And I have all those values. Now, again, I look at west as negative, east is positive. So hold on here. So here we go. We have A equals, all right, my VF is 0. I have a minus sign that's in my equation. Now, VI, 28 meters per second west. I'm going to put a negative 28 in here because, again, I always say west is negative. I try to stay the same all the time. All right, and that is divided by 3.5. Now, that is going to become, let's see here, two negative signs come together to give me a positive. All right, and now finally, I can find out my acceleration. It's 28 divided by 3.5, which is 8. Nice round number. Huh. Meters per second squared, and it is positive. So that direction means east. All right, so now I can go back up and I can find my net force. So my, oops, let's change size here. So my F net is equal to my mass, which is the 12,000 kilograms, times my acceleration, which is 8 meters per second squared. And of course, to the east. All right, and I multiply those, and so my F net is going to be equal to, let's see here, 9,600 newtons to the, to the east. And there we go, and there is my net force. So I had to use my motion equations again to find my acceleration so that then I can find my net force. And again, it's all tied together, motion and forces, because forces make things move. And so they are obviously related. And you can see that my net force is in the opposite direction of motion because we're applying the brakes, which creates friction, more friction. All right, let's see here. One more. I think it's just like this type of question. All right, so an object with a mass of 15 kilograms rests on a frictionless horizontal table. If a force of 30 newtons right is applied to the mass, what will the velocity be after 10 seconds? Okay, so let's get some of my values down here. My mass, M, is equal to 15 kilograms. My applied force. So I have an applied force, so that is my FA. And that is equal to 30 newtons. Again, it's a vector, so it is to the right. All right. What will its velocity be? Oh, after 10 seconds. So again, there's our time. T equals 10 seconds. We want to know that final velocity. VF. Whoops, question mark. This kilogram mass is at rest. All right, so that is telling me that my VI is equal to blank. Oops, sorry, VI is equal to 0. It's at rest. All right, so we have all this information. Now, I have my force applied, I have my mass, I want my VF. Now, if you look at our last equation, where I used A equals, we're kind of working backwards here. A equals VF minus VI all over delta T. Now, I have this. I don't have the A, and I'm looking for the VF. But I can use F net is equal to MA to find my acceleration. So I'm working backwards. I'm going to use my F equals MA formula first. And so, well, I'm going to plug in my values here. And so my F net is 30 newtons to the right. All right, my mass here is 15. And of course, I want my acceleration. Oops. Cap log. There we go. All right, so I'm going to divide both sides by 15. And again, my acceleration is a vector. I'll put that in there. Well, 30 divided by 15 with direction, my acceleration is going to be 2 meters per second squared to the right. So now I'm going to put that information up here. All right, so let's have a look here. So I have A is, again, I go with right is positive, left is negative. All right, so I have acceleration is 2 is equal to, I don't know my VF. My VI is 0, and my delta T is 10. Now, this is something we had quite often. I have a number equaling a fraction. I create a fraction equaling a fraction. Now, what that gets me is 1 times VF minus 0. Well, VF minus 0 is VF. 1 times VF, VF. 2 times 10 is 20. The units, meters per second, because it's a velocity. It is a vector, and because it's positive, that means the direction is to the right. So now, because of Newton's second law, we are absolutely being able to tell, if we know the mass and we know the force applied to the mass, we can determine the acceleration, which then now allows us to use motion equation to predict what the motion of that object will be. So that is how our Newton's second law works.